In this video, we're going to consider the inverse Laplace transforms using Heavyside functions. Inverse Laplace transforms using Heavyside functions. Generally, whenever you have e to the minus cs, e to some constant times s, times a function of s, it's the inverse Laplace transform that's going to result in a Heavyside function. And this is a theorem that's very helpful. And we're going to use this theorem. So let's do some examples. So let's consider this here. And so we want to find the inverse Laplace transform. And we want to apply this theorem. So we want to maybe write this so we can identify the E and then the F of S. So let's write it like this. So this is S to the fifth, by the way. So once again, identify the C. So you can see from the theorem here that C is going to have to be equal to 8. And then whatever is beside this E is going to be your capital F of S. And so now, in order to apply this theorem, we're going to have to find F of t. So find the inverse Laplace of this. Now over here, my table gives the inverse Laplace transform of this as being t to the fourth. The only problem is we need a 4 factorial up here. So in order to get that, we're going to have to multiply by 1 over 4 factorial. So over here, do 1 over 4 factorial. And these should be, I'm sorry, these should be inverse Laplace transforms here. S to the fifth like this. So then we can use the table and to say that this is going to be f of t is going to be 1 over 4 factorial. And the Laplace transform, inverse Laplace transform of this is going to be simply t to the fourth, like this. So now we have everything we need to apply our theorem up here. So we can say f Laplace transform of e to the minus 8s over s to the fifth is going to be equal, according to this, h of t minus c, and we said that c was 8, times our function f of t with t replaced by t minus c. And so, of course, c is 8 again. So that means that in our function here, we're going to put t minus 8 in for t, huh? So 1 over 4 factorial t minus 8 to the fourth, like that. And that's it. So let's do another example. And keep in mind, we'll keep our theorem handy here that we want to use. So let's do this example here. Want the inverse Laplace transform of e to the 5s and again, this is a 5 and that's an s over s squared plus 4. Once again, rewrite these so they're a little bit easier to see what's going on. E to the 5s like this. And then 1 over s squared. And I'm going to rate that as 2 squared because this looks like something we're going to look up in the table. And I remember the Laplace transform, we have one that sort of looks like this. So once again, identify your C. So you can see from our theorem here, we want this up here to be minus CS. So if we use this, then C has to be equal to minus 5. Then this is our capital F of S here. And so we're going to want a small f of t, so we have to take the inverse of Laplace. Like this. So on the left, we have f of t. Now, once again, if we want to do this from the table, if there's a 2 here, 2 squared here, there's going to need to be a 2 up here. So in order to get a 2 up there, we're going to have to just put it in. But then, of course, we have to divide by 2. Like that. I keep losing my minus ones here. So those are both good inverse Laplace. And so once again, if you look this up in the table, this right here is going to be sine of 2t. Like this. So now we have all of our parts and we can apply the right hand side here. So this is going to be inverse Laplace transform of e to the 5s over s squared plus 4, and just substitute everything in, equals h of t minus c, but c was minus 5, so it's going to be t plus 5. And then f of with t replaced by t minus c, so it's 1/2 sine of 2, where t is replaced with t minus c, but c was 5. It was minus 5, so it's going to be t plus 5 again here, like this. And that's your answer. You could maybe, if it looks a little bit better, maybe if the 1/2 was in front, maybe. And if you wanted to distribute the 2, you can. And that's our answer.